Welcome everyone to this special edition of the Spectral Geometry in the Cloud seminar, which is transformed into a conference for the occasion. It is the fourth installment of Young Researchers in Spectral Geometry, and we have the pleasure of having three people today who will speak about their research. And without waiting anymore, let me introduce the first speaker. So Stine Berge will speak about, she's from Hannover, and she works in Hannover, and she will speak about convexity properties of harmonic functions on Riemannian manifolds. And the virtual floor is yours. You can go ahead.
Thank you for the introduction, and thank you for organizing this lecture series. I've really enjoyed many of the talks here in spectral geometry in the clouds. So I'm going to talk about convexity properties for harmonic functions on Riemannian manifolds. And this is mostly based on the work I did at my PhD thesis. In my PhD thesis with my advisor, Evgenia Malenikova. In this presentation, I'm going to have these three main points. So first of all, I'm just going to go through the classical convexity result for harmonic function in the Euclidean case. And thereafter, we are going to see how we can extend this convexity property to eigenfunction and look at some other similar results for instance, elliptic equations. Thereafter, we are going to move to the second part of the title, namely Riemannian manifolds, and look at the result in Riemannian manifolds. And finally, I want to present some of my own work when it comes to looking at other surfaces and stuff like that, but more on that later. Okay, so the first thing is that, well, in this talk, we are going to let H denote a harmonic function defined on some ball in this first part in Rn. And just for convention, I choose the Laplacian denotes the divergence of the gradients without the minus in this talk. So then we can look at the L2 norm over growing spheres. And what Almgren noticed was that this function h here satisfy the following kind of equivalent relationships. So first of all, if you take the logarithmic derivative of h and multiply by r, which we are going to call the frequency, this is an increasing function. And equivalently, you can ask that this weird combination of h here is convex. And if you actually take the second derivative and look at the kind of convexity inequality, you end up with this convexity inequality. But if you have some kind of convexity, it should imply some inequality for the original function h. And in fact, if you actually look at this being convex and interpret it, you should have some kind of inequality like this. Okay, so now we have some weird kind of inequality, and now I would just want to point out why this matters, or why I think this matters. And the first reason is that this will imply kind of the propagation of smallness, or so-called propagation of smallness for harmonic functions. So for instance, if you know that your harmonic function is very small here, and you know that it's bounded on some very big ball, then you know that on this middle sphere here, it should also be very small. So you can kind of propagate smallness a bit out. The next thing is that it's probably the most difficult way I know to show unique continuation, at least in the strong unique continuation. So this is just that, well, if you are 0 on the neighborhood, then you can move the 0 to be on a bit bigger set, and just doing this, you will get that your function is identically 0. Indeed, this kind of inequalities are often called quantitative unique continuation. I refer into kind of this being some kind of stronger unique continuation. And finally is the fact that this frequency function controls the vanishing order of H. So you have some results that say that if you know what this guy is, then you have a good control over how fast your harmonic function can vanish. So in the case of homogeneous harmonic polynomials, then we know that the result is sharp. And in fact, if you do the calculation and see what the frequency is, then you have that this is simply just the degree of the harmonic polynomial. So the homogeneous harmonic polynomial plus some things that depends on the dimension you are in. And since we have a constant function here, then this inequality here becomes an equality. In fact, you wouldn't really need this kind of a very strong, in the case of a homogeneous harmonic function, it's very easy to see that you have this. Okay, but even when you don't have a homogeneous harmonic polynomial, then you can kind of interpret these kind of inequalities as being that the frequency tells you what kind of degree the function has. And to make this precise, if you take some s less than r, then this ratio here is bounded by kind of this polynomial to the power of the frequency, and you have the bound above and below. Okay, so now I want to move to the second part of my talk, namely the extension to eigenfunctions. And again, we have now U is an eigenfunction on a ball. And in this case, what I want you to notice is that if we have an eigenfunction, there is a way to embed it into a higher dimensional space, obtaining a harmonic function. So if you take this new variable t here, and let it just be a multiple of, for instance, e to the power t k, where k is the square root of the eigenvalue, and this function here is a harmonic function. And then we can kind of modify the h function from previously. It's like that instead of integrating over spheres, we can integrate over balls. And just a quick note, the reason for integrating over balls is that integrating over spheres would not work very well when it comes to unique continuation, because there exist eigenfunctions being zero on spheres, which are not identically zero. In this case, we have that this modified h function satisfied this very similar kind of convexity result. Okay, so the proof here is, as I kind of alluded to in the previous above, is that it's just using this kind of harmonic extension technique. Okay, so the first result I want to say, which is my own, or together with my advisor, is that this constant in the previous slide here, you cannot have anything that grows slower than this e to the power kr. And the way to prove this is to use separation of variables, and then the radial part will be kind of a Bessel function, and the spherical part will be a spherical harmonics, which we will kind of ignore. And what we can show is that the goal is to show that for this Bessel function, we cannot have anything that grows slower than this e to the power ckr. And the way we do this is basically using Sturm-Liouville comparison theory and kind of compare the Bessel function for a small radius with this r to the power cm. Just before we move on to Riemannian manifolds, I just quickly want to go through some other very similar results. So very classical, we have a Garofalo and Lin results, which I have slightly simplified in this talk. So let's say that U now solves this kind of elliptic equation, where this mu here is the Lipschitz function, and we have also that this Lipschitz function is 0 is equal to 1. Then we can define this h function just with this weight here, and also this dr here, which will kind of take the place of the derivative of h. And in this case, we have that the following function here is increasing for r less than 1. And just like quick note, Garofalo and Lin shows something a bit stronger in their article. I just like kind of restricted it to a special case. But this kind of results also works for elliptic equations. And Kukavica has also a result for this kind of Schrödinger equation, where V is then a bounded positive potential. And again, we can define this h function with the same weight as in the last slide. And having d here as kind of, again, replacing the derivative of h in the unique continuation inequalities, then we have that this function here is a non-decreasing function for some r less than some number, and this being almost like the frequency for harmonic functions. Okay, so then I want to move on to Riemannian manifolds. So in my case, I'm going to work in some very special coordinates, namely the spherical coordinates. And this means that I will choose a point P in my manifold. And then I will let R of X denote the radial distance from this point P here. And this SR here is going to denote the the geodesic sphere with this radius R here. So in this case, we can define the divergence, we can define the gradient, and we also have then the Laplacian, and we can define a harmonic function just the same way as previously, at least on kind of paper. So we have the Laplacian for then respect to this metric. Okay, so then again, we have this h function here, now just with everything with respect to the manifold. And if we want to get some kind of convexity results, we somehow need to control these derivatives of this h function. And there's really two ways this h function can grow. One of the ways is that this harmonic function grows with respect to the spheres. And the other one is that volume of spheres grow with respect to the radii. So if we take the derivative, then here we have the part where h grows with respect to the radius. And this Laplacian of r turns out to be how fast the volume of spheres grows with respect to the radius. So we need some way to control this guy here. And if we try to take the second derivative, because it's some kind of convexity, then we end up with some kind of very long expression. But again, this part here is kind of the function. So it should not be like a squared here. It should just be h times h double derivative r. But anyway, so we end up with this guy here, so which we also need to control here. But a new term is this radial derivative of the Laplacian of the radial derivative, the radial distance function. Okay, so the way we are going to control this kind of Laplacian of the radial distance function terms is to use comparison geometry. So there are kind of two ways this can grow. One way is that it does something like grow slower than in the Euclidean case. And the other one is that it grows faster than in the Euclidean case. And this is kind of in these two ways. So if you have that the volume of spheres grows slower than in the Euclidean case, then you would have something that looks like the standard sphere, where you have that if you look at the volume at each of these kind of geodesic spheres here, it's always less than in the Euclidean case. And if you look at the other way and try to do something that grows faster, then you have the example, for instance, with hyperbolic space. And the best model to kind of do this is by crocheting. And I actually made my mother make this thing with the crochet thing. And what you actually does is just to kind of crochet faster or more stitches than in the what you would have in the Euclidean case. Okay, so to kind of make this precise, I will introduce this kind of cotangent function. And in the Euclidean case, or the curvature 0 case, you will have 1 over t being the kind of corresponding to the Laplacian R term. This is going to be the positive case where you just end up with the cotangents. And in the negative curvature case, we are going to get the hyperbolic cotangents. And this term here, so the radial derivative of the Laplacian, we are going to control by this being equal to just the Ricci curvature, and then minus this Hessian squared thing. So what we are going to use is the so-called Rauch comparison theorem. And it tells you that if you have some sectional curvature bound, so the sectional curvature is between this kappa here and bounded above by this k here, then the Hessian of the radial distance function needs to be between this cotangents kappa here and this cotangents k here. And in the case that we actually are in the constant curvature cases, then of course this thing here becomes an equality. And if we take trace of all these sides here, we end up with controlling the Laplacian of the radial distance function with n-1 cotangents kappa here above and n-1 cotangents k here below. So again, if you have this here inequalities being actually equalities, you have equalities here as well. Okay, so using this kind of bounds on the volume growth, Mangobi was able to prove the following kind of convexity result. And in the case that we have the constant curvature, so we have constant curvature, a lot of the term vanish. For instance, this term here vanish and this term here vanish. And in the case that the curvature is 0, which means that we are again in the Euclidean case, we have the same result as we saw in the beginning. So this is just a generalization of the result I presented on the first slide. Okay, so if you try to kind of see what kind of inequality this here result in when it comes to the h function, so not with the derivative, but just with h, you can get it by kind of trying to integrate this inequality here, but it's not a pretty expression, so I will not show it. And so what I want to do in the last couple of slides is to kind of go through how you can do this instead of the surfaces being spheres. You can have other kinds of surfaces and get similar kind of convexity results. Okay, so to get other kinds of surfaces, you need some way to kind of parameterize them. And the way I did it in my article was to choose the level surface, so choose the parameterized family of surfaces to be level surfaces of some function. So if you have some function going to the positive number where I want all the surfaces to be nice, so I will assume that it's a regular function, except possibly at 0, then we can define this kind of, which is going to replace the spheres as being just the inverse image. And also I will assume that this kind of family does not have any strange holes. So I'm going to assume that if I take the inverse image of everything up to time t, then this is, and take the boundary, this is exactly going to be this ST level surface here. Additionally, I want you to notice that if you try to kind of grow these spheres, so you let, or the things that replace the spheres, then this family here will follow the gradient vector field. So this means that you have very good control over how this grows, only knowing how the function behaves. Additionally, I don't want to integrate infinite stuff, because then I don't know if then nothing makes sense essentially in the inequality potentially. So I will assume that this is compact. And finally, just a technical thing, I'm going to assume that this guy here is integrable. Okay, so doing this, we can define the same guy h here, where we integrate a harmonic function, and then we also have some weight here, depending on the function f we chose here. So then we can try to play the same game and try to get the second derivative and just compute a lot of stuff. And what you end up with is that you at some point will need to control the difference between the spherical tangent of h and the normal tangent of h, at least to get the lower bound, but luckily Hermander has a solution to this. So at least you know that there exists some lower bound, even though it's a pain to actually compute. So if you assume this, or you know this, but you find this function here, and you compute what the Laplacian of f is, and get some upper and lower bound, and also something which starts to look like the mean curvature of the surfaces. In this case, you will have the following kind of convexity when it comes to your function h. Okay, so this is all well and good, but it's kind of pointless that I present you a very complicated inequality without any example of any new usages for this. So the final things I want to go through is 2 examples where I actually try to compute some examples. So the first thing is to just look at growing ellipses. So to get the ellipses, I just take a positive definite matrix, D here, and I define my new f function to be the inner product between x and dx. And in 2 dimensions, this will just give me a family of ellipses with constant eccentricity. So then I can kind of just compute the Laplacian of this function f and all the other functions I had in the previous inequality. And in this case, we end up with this inequality here, where C1 and C2 are constants which only depends on D. And in the case that we had chosen D here to just be the identity matrix, we end up with the same inequality as we had in the first slide. And also, if we try to kind of figure out what does this actually mean for the function h, then we end up with a very similar kind of 3 ellipses inequality. So you have the middle ellipse is bounded by the product between a small ellipse and a very big ellipse, and just the square root. And additionally, we can compute the frequency function nh here, which end up being this combination here. So it is actually possible to compute something using the result. The final thing is that I thought that, well, ellipses are essentially just stretched out balls, stretched out spheres. So let's try something that's definitely not a sphere. And what I did is essentially just pick a lower dimensional sphere inside Rn and just take the distance to it. So if, for instance, if you just take a circle inside R3 and take the distance to it, then you end up with growing tori. And just to make it precise, I have written down the exact form here on the function f I get. And what happens is that if you try to grow these tori very large, at some points they will start to kind of melt together. So it starts and then it will melt together. And then you will not have a regular function, which was some of the things I required. So I will assume that I stop growing before they melt together, or have kind of like a conjugate point, so to say. So in this case, we end up with the same inequality as on the previous slides, with just some new constant here. And one thing to note is that in the case that epsilon goes towards 0, these constants blow up. So I don't think it would be possible to get these kinds of results if you try to go through any conjugate points. But yeah. Okay, so I think that was everything. So thank you for listening.
Thank you very much for the talk. We can thank you. So we have time for a few questions. Anyone has any?
I would have at least one. So this result at the end that you mentioned, where the constants blow up as epsilon goes to 0, do you have examples of actual harmonic functions where you have that this growth?
I should have tried to find some, but at least tried something. But no, I don't. But I don't think it would be possible, just because the computing, it's kind of becomes very large, the quantities, when you go towards this point where it's melts together, kind of. But it might be possible. I might just be horribly mistaken, and you actually manage. But yeah.
I mean, I don't think it would mean being horribly mistaken. It just means that it's a technical artifact. Of
Yes. But yeah, it would be nice to actually know that, because this is kind of like a conjugate points, just with different growing surfaces. So if it doesn't work here, it should not work past any other conjugate points. So that would just be nice to know.
Okay, thank you, Jean. Does we have time for another question?
I don't know if Alexandre.
Go ahead, Philippe.
Okay, so thank you. So I had a slightly simple question, but maybe you went over it during the talk. So what is the improvement that you get on your result compared to just, let's say, assuming that any convex, let's say, deformation of a sphere would be sort of like in between a small sphere and a big sphere? You know what I mean? Like if you say every level set is sort of in between a small sphere and a big sphere, like what is the improvement, or why does that sort of comparison not work?
So you're thinking when we are assuming kind of that they are topologically equivalent to spheres, or?
Yeah, just because you're essentially integrating over convex.
Yes, in some sense. Yeah, at least the inside needs to be kind of convex. Not in the tori example.
Okay, okay.
But yeah, in the case that we actually have spheres, then if we try to do kind of, I mentioned the result in the beginning when you have elliptic equations, and what you can do is actually just do change of variables and get an elliptic problem instead. And there it's very similar to kind of what you get with the weight and stuff like that, as I mentioned in the beginning, is very similar to what you get in the kind of case of Garofalo-Lin and these kind of equations. At least when I did the computation for the ellipses.
Yeah, perfect. Yeah, that answers my question perfectly.
But I think it, like, at least in the case of Garofalo-Lin, they assume also that it's at the 0, it becomes it's like the identity, which I don't need to assume when I go to kind of this Riemannian manifold picture, if that makes sense.
Yeah, perfect. Thank you.
I have a question. On slide 9, the first equation on slide 9.
Yeah.
Yes. Yeah. It seems to the Calderon problem. My question is, can we solve it by using Bessel functions or a map like Dirichlet-Neumann?
So are you asking about this specific problem, or so are you asking about if we can solve the Schrödinger equation? Are there any other of the equations here? Are you thinking about this one? I'm sorry, I don't think I catched your question.
On this equation, we want to determine v of x, but we have another condition like on boundary, Dirichlet-Neumann condition. Not only this equation, it's a boundary value. Yes, I only see some of them. Some people can solve it like by using Dirichlet-Neumann, but I want to solve it by using the Bessel functions.
I don't think so. If you want to solve it by using kind of this kind of separation of variables, I assume, or when you're talking about you want to solve it by using Bessel functions, are you talking about using separation of variables? Or because in this case, I would think it's much easier if you, for instance, the potential was radial or.
So
Okay.
I'm really sorry to be interrupting conversations, but we are going to take a little break and to set up the next speaker.
Okay.
We can. Sorry, you guys can keep on chatting.
Yes.
Afterwards.
Yeah. Okay.
Well,
of course.
Thank you again for the great talk.
Okay.